All right, Chem Squad, the next topic here is potential energy diagrams, and you're going to spread this out across 2 pages in your notebook. Let's go ahead and get started on this. And before we even look at what an energy diagram is, we need to understand what enthalpy is. And enthalpy is going to be a term that is used to represent the total energy within a reaction. So we're looking at the overall energy from everything put together at that point in time. And it's usually going to be, it's always going to be represented with a capital H for enthalpy. And during a reaction, this amount, this total energy or enthalpy, will change depending on what is happening in the reaction. So the reactants and the products typically have a different amount of energy because we are moving the bonds around. So the bonds have a big effect on the total energy when we look in terms of going through a reaction. So a couple key things to remember. During a reaction, energy is found inside the bonds. We talked early on in the year about this being a potential type of energy. So whenever we talk about chemical energy, we're talking about the energy that is inside the bonds between atoms. Energy is also found in the movement, and we focused on the key term for temperature and average kinetic energy at the beginning of the year. So that also provides some energy to our reaction. And this is going to be the new thing we're going to look at, which is called activation energy. And every reaction, in order to get started, needs a little boost or a kickstart of energy. So a lot of times, the reactions we witness just take enough energy from the atmosphere or the environment around them to get started. Or you might think of it like it's the spark that gets things started. So sometimes if we have a reaction, we'll need to give it a spark or a little bit of flame. That's the activation energy to get it started. And all of those are taken into account when we think about enthalpy. So enthalpy is the overall amount of energy in the reaction. So not just one substance, but everything put together. All right, and taking enthalpy a step further, you're going to see sometimes it's represented as a delta H. And whenever we see that delta, that means we're looking for the change. So if we're looking for the change in enthalpy, we're going to have to subtract something. So whenever you get used to seeing a delta and then anything else after it, any other variable after it, you're going to be subtracting from somewhere else. And delta H is going to be taking the enthalpy or energy of your products and subtracting the energy of your reactants. When we do that, if we end up with extra energy, so products minus reactants, and it's a positive delta H, that means there's extra energy left over, and that means we had to put energy in. It's an endothermic reaction. If we calculate our delta H and we get a negative value, that means that we have a larger energy in our reactants, and that would be an exothermic reaction. And we'll see what this means when we look at our charts here in a second. All right, so on the first page, draw this graph big so it takes up most of the page that was provided to you in your notes. Remember, we're going to use 2 pages. So take a second, pause this, and draw in this entire graph, and then we'll talk about what it actually means. Okay, so the first thing we're going to label is that you're going to label up above that this is considered an endothermic reaction. And we'll talk about how we know that here in a second. But let's look at this graph and figure out what it's telling us. So we have what's called the reaction coordinate along the x-axis. Another way to say that is reaction progress. So this is the progress of a reaction from start to finish, and that's kind of what we're mapping out along the x-axis. And the y-axis says potential energy. So really what the y-axis is measuring, if it's measuring the potential energy, is that it is measuring our enthalpy. And remember, enthalpy is going to be an H. So our line that we follow here, so starting at the beginning right here and following it up, this is the enthalpy or the energy through the reaction as it changes. Okay, so now think if we're going to look at this as reaction progress, every reaction starts with your reactants at the start, and we form our products at the end. So when you see these energy diagrams for a reaction, you're always going to have a starting point that's going to have a little bit of a flat line and an ending point that's going to have a little bit of a flat line. That starting point where you see that flat line is going to be your reactants. That ending point is going to be your products. So the purple area we just circled, or this A vector that we're looking at here, that is the energy or enthalpy of your reactants. Whereas D is the energy or enthalpy of your products, because that's what our reaction is ending up with. All right, some other values we have in here. So we have C here in the middle. If you look where C is measuring between, it's measuring between our products and our reactants. So C, if it's going between those, is actually measuring the difference between our products and our reactants. So C, this area here, is going to be considered your delta H. And so looking at that, if we were to measure our difference, our products is greater amount of enthalpy than our reactants. So because of that, if we subtract products, the energy H of our products, minus the energy or enthalpy of our reactants, we get a positive value. So since this is a positive value, that's how we know this is endothermic. The way I personally look at it is I look at which side has more energy, my product side, and in order for that to end up having more energy, it's going to have to take in energy compared to the reactants, which makes it an endothermic reaction. Okay, the other key part we need to look at in these graphs, so this is the new part, is called the activation energy. And remember, every reaction needs a boost of energy to get started. So the reactants already have a specific amount of energy. But in order for us to break those bonds and form new bonds as products, we have to input a little bit of energy. And that's actually not labeled on here. So we're actually going to add this in there. This energy, to get to this peak here, that is your activation energy. So that's the amount of energy to get those bonds to break and reform, to get it started. So think of that as your spark. All right. Now, in a short period of time, in between your reactants and products, you get a compound or the mixture of things that's called your activated complex. So this is kind of an intermediate spot between the two, where you have not quite a reactant, not quite a product, and that's called your activated complex. So the peak, the B going from the bottom all the way to the peak, that's the energy of your activated complex. Okay, so this represents an endothermic reaction because our reactants have a lower amount of energy than our products, and the new one we just added was the activation energy going from your reactants to your peak. All right, on the other page, next to it, take a second and draw this graph. Note it looks very similar. We're just going to have one little change. So draw it nice and big. So give yourself a second, pause the video. All right, so let's go ahead and label this graph. So if the other one was endothermic, this one's going to be exothermic. So go ahead and title this one exothermic, which again means that we are releasing energy. And notice the trend for this one is different. Before, our reactants were lower than our products, but this one we have a downward trend overall, which means our products are lower than our reactants. Now it's still set up the same way. So A again is going to be the energy of your reactants, and D is going to be the energy or enthalpy of your products. This one's labeled a little bit differently, so they're going to switch up the labeling, and you're going to have to be able to figure out what's what. B, in this case, is going to be your activation energy. Notice this one doesn't seem to take as much energy as it did before. C is the energy of your activated complex. So that's the area in between. And this one doesn't have a delta H, but if we were going to label where our delta H, or the difference between our reactants and our products, it would go between these two dotted lines. So this area here is your delta H. Now, if we were to actually calculate our delta H, you can see that because our reactants is higher than our products, amount of energy, remember it's products minus reactants, this would get us a negative value. And since we would get a negative value, that tells us it is exothermic. Or you can look at it like the reactants have more energy than the products. So after we have formed our products, they don't require as much energy. There's leftover energy, and that's going to be released. One last thing that tends to come up with these, and this is actually from biology, is that if you add a catalyst to a reaction, you can cause the reaction to speed up. And this happens because when you add a catalyst, you lower your activation energy. So the purple line here would be what happens if you add a catalyst. And a catalyst, if you recall from your bio days, is just an enzyme used to speed up a reaction. The way it works is that it decreases your activation energy. So it takes less energy to get your reaction started. That's it for now for energy diagrams. Make sure you have them completed, nice and big, color-coded in your notebook. Bring them to class and bring any questions. Chem Squad out.